Now, this is the last topic of this section of this course, this kind of the culmination point, right. So, the last topic is vector fields. First, let us go through the introduction. At first, we will go through the familiar vector fields like gravitational vector field, electric field as well as the magnetic field. Now, let this E represents the earth. So, the gravitational vector field has this shape, you know, these are the field lines. It attracts the other masses towards the center, and we know that if you take any point on this curve or on this surface, because this is 3D, on this surface, all the points on this surface have the same potential level. If you take MGH, you have the same H. Therefore, this is called the equipotential surface, and you can make this important observation. These field lines are always normal to this equipotential surface. They are perpendicular. The case is the same with electric field. If you place a positive charge like this in the space, the field lines emanate from it. The field lines leave the charged object if it is positive. Now, again, if you take a surface of which all the points have the same distance from this point charge q, this is the equipotential surface, and you can also make the following important observation. This surface is always normal to these field lines, and this is the equipotential surface. And also, the earth attracts all these masses, so it is a sink. All the field lines are towards the sink, and on the other hand, this point charge, which is positive, plays the role of a source. It emanates these field lines. All the lines leave that source. Like it is like this. If you take the sun, I mean all the light rays leave the sun. Therefore, sun is a source. Likewise, here this is a source and this is a sink. This attracts all these lines. Right. So, there are two things. A sink always attracts these lines. Source emanates these field lines. I mean, emanates these, like the field lines leave the source. And the third is the equipotential surface is always normal to the field lines. Now, we will get into magnetic fields. Now, in a magnetic field, if you take this example, if you take a current carrying conductor which takes current to inside this board, even if you use the right hand rule, if you take a screwdriver and rotate it in this direction, the rotation gives you the direction of the field lines. So, you know that in the case of this magnetic field, not in every magnetic field, but in this particular magnetic field, you can see the field lines form closed loops, right. And also you know that in the case of a magnetic field, we do not discuss a potential. You have a potential in gravitational field, you have a potential in electric field, but you do not have a potential in magnetic field. The reason is this, in this case in particular, say you start from this point. When you move along this curve, there is a work done by the vector field, by the magnetic field. and finally you arrive at the same point. So, initially there was some energy level. After some work done, still you come to the same point. So, what is the energy level attached to this point? Is it the previous energy level or is it the present energy level? So, it leads to an ambiguity. We do not know what energy level is attached to this point. Therefore, we simply do not talk, do not discuss any energy level in the case of a magnetic field. You know, the energy level at a given point is called the potential, energy. But here, since you cannot attach an energy level to a fixed point, therefore, you do not, there is no potential level pertaining to a magnetic field. Main reason is that there are loops here, right. So, you can make these observations. Field lines are normal to the equipotential surface, and at the same time, when a rotation exists or when there is a closed loop, a scalar potential, because potential is not a vector, we particular in this case we call it as a scalar potential, cannot be defined. Now, in general, a vector field is something like this. You know, in all these three cases, everywhere, if you take any point, there is a vector, there is a magnitude to that vector, right. Like for example, here, when you are closer to Q, the strength is higher. When you move further away, the strength is lower. Therefore, if you draw the strength by a length, if you represent the strength by a length, by the length of an arrow, here arrow should be longer towards the, when you move further away from the charge, the arrow can be shorter. At the same time, when you move here, probably along the equipotential surface, you have the same magnitude, but you have a different direction. So, everywhere at any point, you have some vector with certain magnitude and a direction. So, a vector field is generally something like that, like a fluid flow or like a electric field, magnetic field. Everywhere there is some vector, but the direction may be different, the strength, field strength may be different. So, that is something called a vector field. In general, it is defined everywhere. Therefore, a vector field is, can be modeled something like this. This is an example. In R3, at any point x, y, z, you have, you can define a vector field like this. You have some magnitude and some direction because of I, j and k. For example, if you take this one, at 1, 1, 2, what happens is you plug in x is equal to 1, y is equal to 1 and z is equal to 2. So, you will end up with I plus j plus 3k. So, it has a certain direction. You can find the unit vector and get the direction. And if you want to find the magnitude at that point, you know, if you have a vector like this, to find the magnitude, you take all these three components, here 1, 1 and 3, square them, add them up and get the square root. That is how you find the magnitude of a vector in 3D. So, you will end up with square root 11. That is how you get a magnitude of a vector at a given point. So, likewise, if you substitute the coordinates of another point, you can still get some magnitude. So, everywhere it has a magnitude, everywhere it has a direction. So, that is something called as a vector field. It is like a paddy field. In a paddy field, any point on the field, you have some like paddy tree, they are everywhere. So, it is like here everywhere you have some magnitude and a direction to the vector field, right. It is everywhere, that is what it means, right. Now, let us see what we are going to discuss in this section. So, in this endeavor, our attention is focused to the following topics. First, there is an important operator called grad operator. Sometimes we call it as Nebel operator, right, or del operator. There are basically three names to that. Here we first address the solenoidal vector fields and then irrotational vector fields. And then the work done by a vector field in 4.3. Here, when you find the work done, you encounter a special integral that we haven't encountered yet. That's called a line integral. A line integral is a simple integral with one integral sign. However, in the integrand, you have all three variables. So that's called a line integral. And when you find the flux through a surface, now it's of course it has, since the domain of integration is a surface, you have two integral signs. However, since you are in R3, you have all three variables. So they don't match, two integral signs and three variables. So that's called a surface integral. When you want to find the charge inside the closed volume, you get a triple integral with three variables. That means it's simply a triple integral, like even though we call it as like here line integral, surface integral, volume integral, the volume integral turns out to be simply a triple integral. So there's nothing much to discuss here, but some attention should be paid to these two, in particular in B, to find the flux through a surface. You need to deal with the surface integral. A surface integral is something little tedious compared to the other two. Okay? Now, finally, we get into theorems. There are basically two theorems, and there's another theorem called Green's theorem. Green's theorem is simply can be derived from Stokes' theorem, but when initially Stokes' theorem was introduced, it was proved using Green's theorem. However, now since we have Stokes' theorem, we don't have to go back and address Green's theorem. Therefore, if we have time, we can possibly as a subset, as a special case of Stokes' theorem, we can consider Green's theorem. Otherwise, these two theorems are good enough for us, sufficient enough for us. In Stokes' theorem, you connect a line integral with a surface integral. Still, we don't know what they are. We have to first go through this one. In divergence theorem, you connect a surface integral with a volume integral. Okay. We will see what they are in forthcoming videos. Okay. Thank you.